All right. Good evening. My name is Akshat Mishra, and we are back here with 30 days of machine learning. Quick overview. My name is Akshat Mishra. I'm a third year BTech student with a specialization in data science. And just to practice and to keep a good check and a good log about all that I've learned till now in machine learning, I decided to make a repo. 30 models for 30 days, each increasing in complexity as we go forward day by day. Uh, I will attach the link of the repo, which anyone can see down in the description as well. But for now, let's continue on with day three. So for day three, what do we have here? House price prediction. Now, I initially didn't want to like even make a video for this or make this initially because this is the most fundamental, the most basic or naive problem statement that we can have in basically the entirety of machine learning. This is like textbook. You can see some of this copied from Kaggle straight away as well. So this is not that important for anyone who's not a beginner, who's at the intermediate or advanced stage. You can skip past it and go on to day four. But I'll say that if you are a beginner, this is a good place to start because I myself started from this. And just a quick note, so I won't be teaching here. Like if you understand that, I'm still just a third year student. I'm not a teacher in by any chance. But I'll try my best to explain the approach that I use in all of the machine learning problems, so that we can just get an idea about how to handle the entire pipeline. And yeah, let's just go on forward with it. So first things first, house price prediction. It's pretty simple. We have some features given to us. In the data set, we have the California housing data set. Okay. You can find this data set built within the sklearn, within sklearn library itself. So there's no need to download the CSV file and go through the entire hassle. It can be found very easily. And we are given a few features. So you can see median income is given of the individual. For example, if I'm buying, the house income is given, house age is given, which means it might be a house which is not new. It's an old house that people have lived in before. Number of rooms, bedroom, population, how many people are living in, all of these things, basic features that we can get about any individual and a home, which gives us an idea as to what will be the pricing of the house. That is what we have to predict. So it is a typical, very typical supervised machine learning problem. Supervised meaning that labels are present. Now, what are labels? Pretty simple. So labels are nothing but like the headings. If you want to imagine, like in layman's terms, labels is going to mean heading. So like here I know that I have some number of features which I can maybe say as X. So these features, median income, house age, all of these features, these are going to be my X. Okay. And using them, I have to predict Y. What is Y? What is Y? The price, which is right here, our target variable. See the target variable. So I have to predict Y using X. So this is like straightforwardly mapped onto a linear regression problem. It is one of the most fundamental problem statements that we can ever see in machine learning. And it basically wants us to find the best fit line. For example, we have got something like y is equals to mx plus c. That is the equation of a line. So where m is the slope and c is the intercept. So that is exactly what we're doing. We want to find the best fit line in order to have an idea as to where the future prices of homes might lie. And we do that based on some historical data, which is already given to us in the data set, which is the data that I showed you right here. Okay. So this is it. It is very linear, very straightforward. So we'll move on slowly. Uh, okay, moving on. This is the pipeline that we implement. This is going to be the pipeline in the entirety of the series. Okay, it's simple, it's elegant, it's beautiful. Uh, yeah, maybe if the model is complicated, like for a deep learning model, there might be a few more steps in between. But yeah, this is the usual pipeline. So we have the raw data set right here. Let me just go on to the code. This is the code right here. So, we have got The library is implemented first of all, typical NumPy and Pandas, the greatest. We have got matplotlib and seaborn both for the visualization. sklearn, like I said, until we head on to deep learning, sklearn is going to consist of everything we need. Supervised machine learning, unsupervised machine learning, everything we can import and we can get from sklearn itself. From deep learning, we'll maybe requiring TensorFlow, PyTorch, stuff like that. But till then, nothing. Everything is sklearn. Okay. So these are the metrics. These are the three metrics that we use. I'll be discussing them in detail, but they're different from the classification metrics. Primarily, we use mean square error and R2 value, R2 score as the metrics in here. This is how we import the data set. So usually, the data set is implemented like pd.read CSV, and then we upload the data set right here, and then copy the path and paste it here. So we have not done that because this is available in sklearn itself. This is how we can implement it. No need to memorize all this. This is basic code available in the standard documentation of sklearn. Okay. Then we sort of declare the data set. So this is how the data set is declared. Okay. Data frame means that the data set has now been converted to a table form, which we need because, how else will we be targeting the data? Okay. And then, of course, like I said, we have a target variable, and then we have the independent variables, which help to predict. So the price here is the target variable. Okay. We just declare it as housing.target. So now the basic data stuff is done. Now we go into the EDA, one of the most important parts of the pipeline. And I think I specified this in the video for day two as well. EDA is never for the person in question, which means that it is not going to go to the organization or go to the company or the client. It is always for me. And by me, I mean the engineer in question, whosoever is playing with the pipeline. You can never build a model without looking at the data. The data is what governs the entire model. Okay, there are little people for that. You know, getting us the data. Data collection is like one of the first steps in any data science pipelines, because everything in a model, how the trends are going to be, everything is implemented, is dependent upon the data. So we have to look through the data to find similar patterns and to get an idea as to what we are dealing with. So for that, we have the data right here. So I've copied the code somewhere else so that I can show it to you. First of all, we go and do the df.head. It returns as the first five rows. This is again very novice like, very typical. So when I run this, I will get the first five rows of the data set. Let me scroll down. See, first five rows. Simple. Median income, these are the features, all of them. Price I have to predict based on what? Based on all these. Based on, all of these features. I have to use all of these to predict price. Okay. And for that, I am using historical data, which means data which has been already collected for me and given to me spoon fed in table form. Okay. So this is just to get an idea how the data looks like. Very basic step. Now we move on to get the shape of the data, which means X comma Y. How many samples are there? How many features are there? Bit typical, boring stuff. Oh, massive. So this data has 20,640 samples, which means 20,640 rows, and only nine features, which means that, these ones, these are only nine. These, median income, house age, these are nine in number. Okay, simple. Then we go on to df.describe. We did this in the last video as well. Df.describe gives us an idea about, the basic statistics of the data, the maximum, the minimum, the mean, median, latitude, longitude, all of these. So this, count how many numbers do we have for the median income. It's going to be 20,640. Standard deviation, mean, median, typical math stuff we can do to get an idea about the spread of the data. We go on to check for the missing values, which is a very important part because missing values, uh, they just destroy the model completely if they're not dealt with. So it is very important to deal with missing values. So we go on and run this, and df.info gives us an idea as to what is the non-null count. Okay. So if there was any element, any feature which had a null value, this would give us some value. So the non-null count is 20,640, which means that there are no null values in this data set. So it's a pretty easy problem to implement. Comment this out again. Feature correlation, again, something we did in the last video. So, uh, these features that we have here, median income, house age, average rooms, these are independent features, which means that these are not the features that we are predicting. We are actually predicting the last feature, which is price. But the thing is that from 0 to 7, median income, average rooms, these features might be correlated with each other, which means that one's value might depend on the other for some reason. It might not. Okay. It's like correlation. So, let's say there are two statements. I say that tomorrow it is going to rain. Okay. That is statement number one. And then, or event number one. And then tomorrow it actually rained. That is event number two. So these two statements are 100% correlated. Why? Because I said it is going to rain and tomorrow it didn't rain. Now, the rain was not caused due to me saying it. Okay, because I don't dictate when it rains. But I did say that it was going to rain and it did rain. So the two statements are 100% correlated. This is correlation. It's a very important statistical concept. I think it was taught to us in the fourth semester in probability and statistics, the typical engineering math. Okay. So to see as to how our features are correlated, we do this and we plot a heat map of it, a heat plot. It is available from the Seaborn library and it will be visible in a moment. Yes, there it is. There's the plot. So, the darker it is, the stronger the features are going to be correlated. Okay, let me repeat. The darker it is, the stronger the features are going to be correlated. So, this is median income, this is median income. So, median income with itself has a 100% correlation. Like I said, that when I said tomorrow it is going to rain and it actually rained, these two statements have 100% correlation, which means a value of 1. Similarly, median income are going to have, they're the same feature. They're going to have a 100% correlation, which is why you see this diagonal, this diagonal right here. This diagonal has all of the features as red. Okay, so this you don't even need to look at. You can look at this orange one right here. Average bedrooms and average rooms, they're very correlated because, if there are 5 rooms, then there's a chance that 3 to 4 of them are maybe bedrooms, maybe not, something like that. Okay, then this price feature is also correlated with median income. This makes a lot of sense because person who's earning, let's say, 50 lakh rupees a year is going to get a house somewhere near that range. He's not going to go for some house which costs 100 crore rupees or something because it just doesn't make any sense. So the house which I am buying is going to, its price is going to be correlated with what I am earning. So it's pretty typical. This is a very good idea to, make this heat map and get an idea about what kind of data we are dealing with. So this is for the heat map. Uh, Now, like we did above with this right here, df.info, it gives us an idea as to what is the non-null sum. But just to confirm whether we did not miss any missing values, we type this statement right here. It is very important. It is the most classical way to check for missing values in machine learning data sets. So df dot is null dot sum. So it returns us the sum of missing values if there are any, and like we see, there are none because the data set is already clean. Zero, zero, zeros. Okay, typical. This is for the EDA itself. Now, like we said, moving on from the EDA, we go on to the feature scaling part. This is probably the only thing to learn from this model because this is so, you know, uh, so basic, so naive to learn from. So yeah. So now for the feature scaling, let me go on to the code and I'll go on to the code and then explain it first without the code. So first of all, let me just explain this statement. Like I said, we have to predict price. So price is Y and everything except price is X, which is why, for X, we have done the df dot drop. It basically removes all the columns. So it removes the price column and keeps all of the other columns. So it's typical. Train test split, very easy. This is all typical syntax. Random state is equals to 42 gives us reproducible results. Test size is zero point 0.2, which means 20%. And training size is 80%. Simple. And it can be 70, 30, 90, 10 as well. I've taken the most typical values, 80, 20. Okay. Now comes the juice, the only juice in the entire code or in the entire model, scaling. What the hell is scaling? Why are we doing it? Why are we doing in this model? Why are we not doing it in any other model? That those are the sort of questions that are interesting. Okay. So let me put it this way. So, whenever we train a machine learning model, it can be any model, anywhere. Take our case, for example, linear regression. So, what's going to happen is that a loss function is going to be calculated. This is again super naive. So, our job is to minimize that loss function because that loss means that values are far away from, the actual values. Our model predicted the value to be 100, but the actual value is maybe 110, 120 or whatever. So that gap, 100 minus 110, 100 minus 120, it can be anything. That is the gap that we need to close or actually remove completely. Okay, so we need to reduce the loss function. Now, in the case of linear regression, usually the loss function that we use is MSE. MSE is nothing but mean squared error. Okay, you can look up the formula, but there's no need. So it's nothing but the summation of y minus the average, and it is squared. So it's squared upon all the values. Now the thing is, if I go on and I run this model and I run it without the scaling, which means I run it normally, but I don't do this step right here, this scaling step. Now that will be horrendous. The model will give us completely, uh, useless results. Now, why is that? So for this, I'll go back to the EDA just to show you something. So, we got this df.describe right here, right? So let me just print this df.describe once again because it's very interesting to see. So when you look at this df.describe, do you see something? Uh, for example, look at the feature house age. What is the mean, the average value of house age? It is 28 point something. Okay. Just look at it. Don't think about the number. Just look at the number. 28 point something. Okay. Now you go on to I don't know, maybe population, which means how many, people have lived there or something. So we go for population and we see the mean value is 1425. Okay, that's fine. Now we go on to average bedrooms. What do we get? The average bedrooms is 1 point something. Okay, fine. What's the average rooms? 5. Now, are you seeing something? Are you observing something? All of these values are different. Okay, I'll repeat myself. All of these values are different. Okay, the median income has different values, house age has different values. The range of these values is completely different. Okay, like this is the minimum value for the median income, and this is the maximum value for median income. Look at the difference between these values. So this is 0.49 to 15. Okay, then if you look at the population, the difference is from 3 to 35,000. So the scale of features, which means, the range of features is completely different, completely off the charts. Now, what do you think? If I train a model on these features, which have a completely different range altogether, what will happen? Disaster will happen. That's what's going to happen. And the primary reason is that, since some features have a very large value, like we see here, population has, the maximum value. Wait, yeah, right here, the average occupancy has a very large value. So these large values, what they do is when we train the model, they are going to dominate the model, which means that, these are the ones who are going to dictate all of the predictions. They might not be the best features for the prediction, but since they have the largest value, when we do the actual math of MSE, they are going to dictate all of the predictions. They are going to dominate the predictions. Now, for this, basically, our optimization will become, very unstable. And what will happen is that convergence, model convergence, like I said, that we have to minimize the loss function, and we keep minimizing it until it becomes exactly zero or very close to zero. So that point is called as the point of convergence. Okay. So convergence is going to be very slow and unstable because these large features are dominating them. So we need to bring them down to a comparable scale, to a scale where all of the features have a similar range. Okay. That is the soul. That is the reason why we do this, why we do scaling. Okay. So this scaling here, if you have studied, again, basic college math, engineering math, probability and statistics, you will know. So this uses the formula x minus mu divided by sigma. So I must have it here. Yeah. See, scaling basically uses the formula x minus mu divided by sigma. X is whatever feature we are dealing with at the moment. Sigma is nothing but the standard deviation, and mean is the average. So when we apply this formula, x minus mu upon sigma, to all of the features, what's going to happen is that the mean of all the features becomes 0 right here, and the standard deviation sigma becomes 1. Now, what this does is it basically brings down the features to a comparable range. Like I said, that without doing that, there's no point of training the model. So now, whenever we try to converge the model, it prevents the large features from dominating the training, and uh, it is basically going to make the model very smooth to run. Okay, so it is very good, and this is a linear model. Like I said, if it was some non-linear model, then scaling becomes even more important. Distance-based models like KNN, again, scaling becomes very important because features have different scales. We need to bring them down to a similar level in order to train the model. Okay, otherwise, large features are just gonna break through, and we are not going to have good results. Okay, so this is it, and this is why the scaling is used. It is very important. And one thing to note, in tree-based models, like on day two, we implemented a random forest model, maybe a decision tree. We never need scaling in these models. Why is that? Why is that? Because in tree-based models, we are creating splits, right? We are creating splits, and splits don't actually base their thresholds on these values. Splits are based on Gini index or entropy, something like that. So we don't need them at all. Here it is like necessary. Now, nothing, we go on to the model training. This is how we train the model. Model.fit is the syntax that we use. These are the predictions of the model. This right here, this is all documentation stuff. You can find this in sklearn documentations. No need to memorize this. Now, the discussion part, the last part, and it is again one of the more important parts of the video. Metrics. Now, for classification, we can get precision, recall, ROC, AUC, F1 score. The thing is, for prediction problems like regression right here, our metrics are not much. They're usually just two. The number one is the mean square error metric, and the number two is the R2 square, R2 score, sorry, metric. So, the thing is, we have used mean square error here, but mean square error has its cons. Let me explain. Mean square error, like I explained, it is nothing but the summation of the square difference between the calculated values and the predicted values. So this is how it is calculated. So it's like the values that we achieved via calculation, the predicted values, and we subtract them from the actual values. Then we square them and we do a summation for all of them. That is the mean square error. It is our loss function, and we aim to minimize it. The less it is, the better our model is going to be. Okay. MSE should be reduced as much as possible. Now the thing is, MSE gives us a good idea. It is like a good metric. It removes all the negative signs because it is squared error. So it is going to square everything. Squaring removes the negative signs, thus making the model, gives us a better idea as to what is happening. All the large errors are penalized. Why are the large errors penalized? For example, I got my predicted value as 10. Okay. The house price I predicted as 10. But the model is saying that the house price is 20. Now, what is the error here? 10 minus 20, which is minus 10. But it's not going to be minus 10. Why? Because it is squared error. So we need to square minus 10. What is the square of minus 10? 100. So did you see how such a small error of 10 got punished and the value increased to 100? Now, what this does is that next time it will make model convergence even easier, because next time it is going to aim to reduce this value of 100. Okay. But like I said, that MSE has its cons. So it's pretty important to discuss those as well. So since we are squaring the values, mean square error might increase the values too much. And it sometimes even makes the values not that interpretable. Like, if like walking, like we know that we need to reduce the mean square error value, but like let's say there's a person just I give him like a blind value of mean square error, that hey, 0 point something, 0.56 is our mean square value. Now that won't mean anything until we look at the data, until we look at the model. So mean square error is not all that interpretable, which means for the human to interpret it is a bit difficult. So for that we do a very simple thing. We take its square root. Okay, we take its square root right here. Okay, and we call it root mean square error. So root mean square error does the same thing. It is just the square root of whatever we calculated. It is much more interpretable, and it basically answers as to how many incorrect predictions we got on average. So this is it. Mean square error as its cons, use root mean square error. There's also an MAE score. It is called as mean absolute error. It is just the difference. Like here we are, squaring the differences and adding them up. So in mean absolute error, we just take the difference and we add them up. Again, it is fine, but mean square error and root mean square error are much more popular and much more interpretable. So they should be used more often. R2 score, very important. R2 score has a mathematical formula that I think again the people who have studied basics of probability will know it, the basics of statistics. So it is 1 minus sum of squared errors divided by the sum of total errors. So sum of squared errors is nothing but the MSE that we are calculating, summation of y minus y dash whole square, where y dash is the predicted values, y are the actual values. And in the denominator, we get the sum of the total sum of squares. So that is the original values minus the mean, and we square it and add it up. So the point is the R2 score always lies between 0 and 1. Okay, always the R2 score lies between 0 and 1. The closer it is to 1, the better our model is going to be. Okay, if R2 score is I don't know, if R2 score is, let's say, less than 0, then it just makes no sense. Okay, it just makes no sense. If it is 0, exactly 0, then model is as good as predicting like an average model. And if it is 1, then it is considered as a very strong model. So the closer the value of R2 score is to 1, we get a better idea. Okay. So this is it. And if we want to see what values we got, so this is the RMSE value that we calculated, and this is the R2 score that we calculated. So of course, the model could have better of these values, but it's a baseline model, so I haven't done much. This is a visualization. I'll just explain it. So results, like I said, that it is very difficult to interpret these mathematical values. Like if I give them to a normal person, they might not even understand it. So just a quick visualization for that. So we make a scatter plot using matplotlib between the actual prices and the predicted prices. So this is how the graph looks like. And, this basically again gives us an idea as to how different the values are from each other. So it is pretty typical. Now this is it. Let me just see what's left. Yeah. These are the metrics, see, MSE, RMSE. These are the values we obtained. It is all available in the repo. You can read it. It's a very simple readme till now. But as you progress to the later on models, I've even added the inference latency, throughput calculation, then more mathematical derivations. Because linear regression, no one needs to see the derivation for linear regression. It's basic math. But as we go on to more complicated deep learning models, I have added everything so that it doesn't feel like a black box to read from. Okay, everything is done from scratch, from first principles. Nothing is, nothing will seem like a black box to you. Nothing will seem mucked up. It's very intuitive, to be honest. Okay. So now, very important thing. I don't think you will see this anywhere being discussed. If it is being discussed, it's a very good thing, but I don't think it is because I didn't find it anywhere else. Very important, very, very important. First of all, the equation. So this is like I said, we get an mx plus c type of equation. W of t is the transpose of weights. So why take the transpose? Uh, because we need to do the multiplication here. Okay. The W matrix will look like a 1D matrix. Like, let's say the weights are point 0.2, point 0.3, point 0.4, point 0.5, point 0.6. Now, this is like a 1D matrix. And X is featured. So 1, 2, 3, 4, 5. Now, how can we multiply them? We cannot multiply them. Why? Because whenever we do matrix multiplication, we need the row of the first matrix to match the column of the other, or vice versa. Which is why we cannot do a WX. We have to do a WTX because WT will make the row of X equal to the columns of W. Then we can multiply them. And this bias term is added so that if this WTX value becomes zero by some chance, bias still exists and the model still predicts something rather than giving us an error. Okay. Yeah, now coming on to the most important thing, the time complexity. No one talks about this. No one even, I don't think so. They do. No one even thinks about this. Okay. So the time complexity, pretty simple. Uh, like in general, we go on for time complexity in data structures and algorithm problems. But since this is a machine learning problem, it will be slightly different, but it carries the same significance. Okay. So, like I said, that every machine learning problem focuses on reducing the loss function. Now, what is our loss function? Our loss function is nothing but the least squares optimization. Okay. Least squares means that we have got mean square error. We need to minimize that error, which means optimize that error. So, we get the mean square error formula, which is nothing but the summation of predicted values minus actual values squared. So we need to optimize that. So, when we optimize that, the mathematical equation transforms and it looks something like this. This is the matrix form of that equation, that specific equation. How is this achieved? You can take a pen and paper and you can just write it out and you will see it. Okay, write the formula for mean square error and then, take this, the mean square error equation and take this equation and solve for W. And you will come to this. Okay. So W are the model weights which we train from. Model weights are they are initialized with random values and then during training their values are updated. Y is the target vector, which is price in this case. X is the feature matrix, which is going to include all the other features except price. So we have got XTX. XTX, XT means the transform of X. So we need to calculate it individually. We first calculate as to what time complexity it requires to calculate XTX, then to calculate the inverse, and then to multiply this XTY term. So it's all individual. So to calculate XTX, which is nothing but a matrix multiplication, it takes us a big O of n into d squared time complexity. Now you might ask, why is that? It is because, first we'll require some complexity to transform, which means, this x will be transformed to x of t. That is going to require a big O of n complexity. And then the multiplication will require d square. So n into d square, which is why this term is achieved. Then we need to take its inverse. Now, inverse again requires cubic time complexity. So there it is, big O of d. And then we need to multiply it with this final term, x of transpose multiplied by y right here. Okay, this term. This term multiplication again, it is going to require a big O of n into d time complexity. We add all of them up and we can get this right here, nd square plus dq. And most of the times the number of samples n is far greater than the number of features. Okay. To show this to you, let me quickly go back here and, you know, give you the shape of the data. So what was the shape of our data? 2000, no, 20,640 to 9. Now 9 is the features here and these are the samples. Okay. Which means that N here, N, number of samples is 20,640, this value. And D, number of features here, is nothing but 9. So you see the difference between them. So when we do something like, nd square plus d cube, this d cube value can usually be ignored because it is a very small value. So we just ignore it, and the dominant term in the problem is nothing but n of d square. Okay. D is the number of features, N is the number of samples. So this is the time complexity whenever we solve a linear regression problem, and this is how it was achieved. So, you can get an idea. And again, coming back to it about this equation, you can basically derive it. This is not this won't even require a derivation. It is just the matrix form of the original, uh, you know, of the original linear regression equation. So you can write it in matrix form and you will achieve this form. This is the time complexity. Now, this is the prediction complexity. Now, what's the difference? So, to do the predictions, we need to multiply the values of the learned weights. Like I said, that the weights are initialized as random numbers, and then the weights are learned. Like, what are the true values of weights? So, we need to multiply them to get the predictions. So, this is how we get it. And for this multiplication, we need nothing but a big O of n into d time complexity, because we have got n samples and big O of d for per sample calculation. So this is it. Linear regression stores one feature and a bias item, uh, you know, for each and every feature. So that takes a big O of d of space. So space is being consumed here. It is not constant. Many people believe it to be constant. That is not the case. So like for every feature, we are calculating this right here. So we have to store this weight, this WT and the bias. So that is a big O of D to store it. And this is about it for the space complexity. Okay. So this was about it for the house prediction model. It is, like I said, it is a linear problem, so it makes it pretty easy, pretty direct to do everything. And maybe this model can be tuned further to get better results. But like I said, it was just a naive model to kickstart the series and just to look at it. So this will be it. Thank you so much, and I'll see you on day 4 for, let me check it out what it is. Day 4 for the decision tree problem on Titanic survival. Thank you so much.